get started. I mean, everybody can see the title and you will.
Okay, thank you. So now I want to talk about something that's sort of faint related, but not really. And this is now joint work with Omar Fazi, Kambis Rouget, and Thomas van Himberg, who's unfortunately not here. So now I want to talk about entropy inequalities, conditional entropy inequalities, and how they relate to these norms that I teased about earlier, and how we can use these norms as a very, I think, neat mathematical tool to prove certain entropy inequalities. Now, the first slide I put is some motivation. I'm not sure if I need sort of this motivation for this audience, but I'm going to go through this sort of anyways. And the applications that I will mention later are quantum key distribution related. A very sort of quantum cryptographic simple task is quantum random number generations. Now, how might we generate sort of a random number is we might start with some quantum state. We get a machine that produces some quantum state. Then we perform some measurement described by this channel. And then we have sort of classical output system that is randomly distributed depending on what the input state and the environment is. But in cryptography, we want to sort of be sure that we have security somehow of this protocol, which means that, say, in practice, what might happen is that our machine might produce an entangled state or might somehow store sort of some information about the state outputted. And then if we perform our protocol, the output system of this protocol is some system XE, where E might know something about X. So this random number might be random to us, but not to some eavesdropper or to somebody who has access to the environment. So in order to consider security of this or related protocols, one way of doing this is to consider sort of minimal conditional output entropies under our protocol. Sort of here, X conditioned on E. And then the types of inequalities that we care about are lower bounds of this minimal conditional output entropy, where we may sort of minimize over all environment systems. We may not. We may also have a channel that has more than one output system, but this type of inequalities. And sometimes we may not want sort of just one round. We may want n rounds because we want to generate sort of n bits of a key. And then we want to ask sort of what happens if I apply my map n times, and do I get something like n times the one round statement? And such statements are usually called IID reductions or entropy accumulation theorems. But since we're beyond IID, we may also ask what happens if we have a tensor product of different maps, and then we get sort of a beyond IID reduction. Yeah, I think we didn't call it this, but I think you should. Okay. And now there's a result by, I think, one of the attendees here that says sort of the entropies that it suffices to consider are certain optimized sandwiched entropies. So just as a quick reminder, sort of conditional entropies we get from parent quantities that are relative entropies. Now, the relative entropy that I want to talk about here is the sandwiched Rennie divergence, which is defined like this, where we have sort of the logarithm of some alpha Schatten norm, which I talked about earlier, of sort of a sandwich quantity between rho and sigma. And then the way we define the conditional optimized Rennie entropy is, let me do this, is by taking the relative entropy between my state rho xe and identity x tensor sigma e, and then I minimize overall potential marginal sigma e. There is also another way to define the conditional entropy starting from the sandwich Rennie, which is the unoptimized, which is often written with the down arrow, and the optimized with an up arrow. Now, clearly, sort of the optimized version is more optimal if we can get inequalities with this because it's optimized, so it will give tighter bounds, but it's also more difficult to handle because it has this optimization included. And now, sort of, one of the purposes of this talk is to highlight I think, very nice tool to work with, these optimized Rennie entropies. Okay. Now, they find applications not just in sort of quantum security of quantum key distribution tools, but also in privacy amplification and in entropy accumulation theorems. And there will also be talk later today about these optimized, among other, these optimized sandwich conditional entropies in the context of entropy accumulation theorems. So these, they appear quite a bit. Now, I want to switch gears a little bit, and sort of we keep the entropy stuff in the back of our minds, but I want to talk about what are called operator-valued Schatten spaces. So just as a reminder, sort of Schatten spaces we can think of as linear maps between Hilbert spaces with that satisfy sort of finiteness of a certain norm, which is the Schatten P norm, which you saw, I think, like half an hour ago. And if our Hilbert space is finite dimensional, then essentially how we can think of them is as matrices, so as n by n matrices with entries in the complex numbers with a certain norm. And now one could ask the question, well, can I define sort of a Schatten norm-like thing for matrices whose entries are not complex numbers, but are again elements in some linear space, so operators, right? So the question here is, we know the Schatten spaces, and they are essentially the space of matrices, n by n matrices with values in C with a certain norm. And can I sort of lift this to get a Schatten-like norm on the space Mn of x, where x is some linear space? You can think of some subspace of some B of k, or some operator space if you know a bit of operator space theory. But I don't think I want to go too much into this. And it turns out that yes, you can do this. PZA is one of the people that developed the theory around this, and if you know operator space theory, sort of this is the natural framework in which to do this. And then we can define what we call the sort of SQ of h comma x spaces, which you should think of. These are my operator valued Schatten spaces. So these are the elements of this space are my linear maps from h tensor k to h tensor k, and the norm I give on this acts as a Schatten Q norm on the H space, but as the norm of X on the X space. So in some sense, we define a Schatten Q norm only on the first part of the system. Now, if you care about sort of how to construct this, then this is quite a bit more complicated, because you need some Hagrob tensor products of certain column and row operator spaces and then some interpolation. But I can skip this because there is a very, very nice formula by PZA that tells you how to compute the norm on this space. And this is called PZA's formula. This is very, very, very handy, because now it gives us a way to compute the norm on this SQ of h comma x, which we just call sort of q comma x, in terms of the infinity comma x norm, which is the natural norm of some amplification of y. And via this formula and via some sort of abstract operator space theory, we also get a bunch of nice properties. So say we let x, our operator space, just be the complex numbers. So then we again consider n by n matrices with elements that are complex numbers. Then we would like that our operator valued Schatten space just recovers our normal Schatten space. And this, for example, this is true. So this tells us sort of that this is a correct or a valid generalization. And then there is some more properties like the Hölder duality and that are satisfied. But the sort of why do we care about this? Why am I talking this very abstract and about these very abstract concepts? And one thing that we can do with this is we can iterate this. So because Schatten spaces themselves can be viewed as operator spaces, you can define sort of Schatten spaces of Schatten spaces. So you consider now linear maps from H tensor K to H tensor K with a norm that sort of acts on the H part as a Q norm. and on the k part is sort of a p-norm. And then via PZ's formula, we get again variational expressions for this norm. Now these variational expressions, for the purposes of this talk, they don't matter too much because they look a bit scary, but they're actually very, very nice to work with. And without these, you couldn't really handle these norms. But now it turns out that for a certain choice of P and Q, what we get is that the optimized conditional sandwich Renner entropy is given as the logarithm of a 1, alpha norm, which is, I think, quite astonishing, that you get this direct correspondence between these entropies and these norms. But what this also means is that via this correspondence between entropies and norms, we can prove a lot of very nice properties for these entropies. So for example, we can get continuity bounds very straightforwardly by knowing that in secret they're just logarithms of norms, or data processing, or monotonicity in alpha. This also all follows very straightforwardly from just properties of these two-indexed Schatten spaces or PZ spaces. And there is a very nice overview article by Salman from 23, where they introduce these operator value Schatten spaces in quantum information theory, and they do some of this derivation. So if you want to read or learn more about this, I would recommend that. Okay, but now we don't just have this correspondence between these entropies and these norms. We can go further. Earlier, I told you that we care also about minimized output conditional entropies, and minimized output conditional entropies turn out to be exactly proportional to mixed norms of my quantum channel under or between these multi-index Schatten spaces. So the minimal output conditional sandwich Renner entropy is nothing but the logarithm of the 1 to 1, alpha norm. And likewise, if we consider if we now put some environment system in and we also minimize about the environment system, then we get that this is the logarithm of the completely bounded 1 to 1, alpha norm. So there is a very, very, very nice correspondence between these entropic quantities, hence also all the inequalities and equalities that we might want to prove of these quantities, and these mixed multi-index Schatten norms. Okay, now I promised I would talk a bit about completely bounded norms. So I want to do this now. So the way that you would usually define a completely bounded norm between operator spaces or between Banach spaces is you take its nth amplification, and then you take the map from mnx to mn of y, and you take the supremum over all n. This is how you define these the completely bounded norm. Now it turns out that this mn of x is isometrically isomorphic to S infinity of Cn, x. So in secret, what this is infinity, x to infinity, y. But now there's a very nice result by PZA that says this index on the ancilla system, it doesn't matter, as long as it stays the same. So in fact, the completely bounded norm from x to y is the same as the supremum over all ancilla systems of some index t on my ancilla system, x, to some index t and my system y. And here, this is not the same as the stabilized mixed norm that I talked about earlier, because for the stabilized mixed norm, you would have x be a Schatten Q space and y a Schatten P space, but then you would also change the index on the environment system. But for the completely bounded norm, you keep the index or the norm that you have on the environment system fixed, but you only change the norm on the system that you care about, your system that your map does something to. And then as an example, you get that the diamond norm is just the 1, 1 to 1, 1 norm, but the 1, 1 norm is isomorphic to just the 1 norm on the whole system. So the diamond norm is just given as the 1 to 1 norm, and then you take the supremum over all environment systems. But what you also get is that if you consider the completely bounded Q to R, S norm, which we saw in the slide before, then one way to compute this is as the supremum over environment systems, and then you take the Q to Q, R, S norm. you could also sort of take your T to be R, and then you get the R comma Q to R comma S norm. But usually sort of this is the nicer form. But what we see here is that sometimes we care about more than two indices, right? And this, yeah, this is a problem because most of the quantum info literature and for some reason most of the operator space literature only explicitly considers two-indexed Schatten norms. Okay. Now I'm going to come back to this. I briefly want to write this or recall this from the last talk, that the completely bounded 1 to P norm, now using these variational formulas, you can sort of plug them in and see what happens, and then it turns out it gives you exactly the infinity comma P norm of your Choi operator. Okay. Okay. Now, okay, I said we have these two-indexed norms, and most of the literature is restricted to these two-indexed norms. But for some of these entropic inequalities, we require more. And in theory, sort of in principle, there is nothing that prevents us from defining arbitrarily many index Schatten norms. We can do 5, 7, 42, whatever. But in order to really work with them, we require these variational formulas. But proving these variational formulas for more than two indices is a bit cumbersome. But we were able to sort of do this for three indices, because for three indices, this is the application that was sufficient for us. But I mean, here you can also take arbitrarily many that you want. And now that we have this sort of generalized PZS formula for, in this case, for three indices, we get a bunch of nice results and chain rules that have applications now in terms of these optimized conditional entropies. Sort of one of the results that we have stated as a result for mixed norms of linear maps is the following. So say you have a CP map that maps two systems QP to two systems RS. And now I consider phi tends to the identity on the right from Q comma P comma whatever norm we have on this system to R comma S to whatever norm we have on this system. And then it turns out that if this map is completely positive, the identity to the right doesn't matter. Now, maybe I should mention one thing here, sort of the order of these indices matters a lot. And the order of the phi and the identity also matters. If the identity was on the left, then this clearly would not be true, because then this would give you sort of the completely bounded norm if you took the supremum, but in general the completely bounded is not equal to the none, so this would not be true. But with the identity to the right, this is true. And now maybe this looks a bit cryptic, but now you can look at sort of this dictionary that I showed you like 2 slides ago between entropies and norms, and this directly gives you this inequality between conditional optimized Renner entropies. In fact, this gives you a bit more complicated looking inequality, which we call sort of an amortized chain rule, and this is normal, or this we just call chain rule, and the other sort of an amortized chain rule. And these have uses in quantum cryptography. And this is not quite my background, so I can't completely tell you where they find applications, but these are sort of useful chain rules to have, at least the first one. The second one seems to be new, so if you find applications for this, please let me know. We'd be interested. But this chain rule, or in particular this equality here, is also very important because it's very fundamental. And with this, we can show many more chain rules and entropic inequalities. And now in the next few minutes, I want to emphasize the one particular chain rule that we use to prove security of certain time-dependent quantum key distribution protocols. So the setup is the following. We have n input systems, Q1 to Qn, and we have n different maps, phi n, that maps Q to two systems Rs. And later, sort of, if we want to consider S conditioned on R. And then we want to see if the whole minimum output conditional entropy under this whole tensor product of these n different maps and some environment is bounded by n times sort of the individual one. So what we would like is something like this. So the conditional here, the optimized conditional alpha up arrow entropy of Sn. Now this is all the systems S together, given all the Rn's and the E under this tensor product of these n different maps. What we would like is something like this is bounded by or equal to the sum of the individual ones. And then if you take all these channels to be the same, you get just n times the individual one. And now you can translate this statement back to norms, and then the norm statement would look like this. We consider sort of the 1 to 1 comma p norm of this whole tensor product, and we want to show that this is the same as the product of all the 1 to 1 comma p norms. And these are completely bounded norms. Now, this is not quite obvious, because if you spell out that Qn is a bunch of Qs and Rn is a bunch of Rs, then what this is saying is that you consider the 1, 1, 1, 1 norm to 1, 1, 1, p, p, p. But here on the right-hand side, this would be more something like 1 to 1, 1, 1 to 1, p, 1, p, 1, p. So the order of these systems is different. And this is why this is not obvious. No? And this we can prove. I briefly want to mention sort of the sketch of the proof of this. And then directly from this equality, you get this, this equality, which generalizes something, or which generalizes the case where all the channels are the same. Sort of, it generalizes the IAD setting of this equality, and as far as we're aware, is new. And with this, we can now do sort of time-dependent quantum key distribution. Now, how does the tool, the proof go? So we need sort of 3 ingredients for this. One is this chain rule that I showed you before, this equality saying that the identity to the right doesn't matter. The second is a very common submultiplicativity of the completely bounded norm. And the third is sort of the fact that if you have 2 systems with the same index, then you can swap them. Sort of indices that are the same, you can combine and you can swap, and they behave sort of intuitively as you would assume. And now, sort of, this is what we want to prove. And the core is seeing that the indices are different, right? So why does this matter? Well, let's start with the case where n is 2, and then we just do induction on n to get the general case, right? Now we consider this equality where we map Q1, Q2 to R1, R2, S1, S2 with these indices. And we can rewrite this a bit, because we see sort of that to get from Q1, Q2 to R1, R2, S1, S2, we don't just have to apply sort of our, okay, this should be phi 1 and this should be phi 2. But we don't just apply sort of phi 1 and phi 2, but we also have to apply sort of swaps on certain systems to get the order of the indices right. And then you can decompose this tensor product of these maps as a product of sort of 4 maps, and then you can use the submultiplicativity, and then it turns out that sort of swapping 2 systems with the same index doesn't matter. So this swap and this swap goes away. And here we have the completely bounded norm of identity times something, but the identity on the left doesn't matter in the completely bounded norm by definition of the completely bounded norm. And here we have an identity to the left and an identity to the right. Again, the one on the left doesn't matter because we have the completely bounded norm, and the one to the right doesn't matter because we've proven earlier that for completely bounded maps, the identity to the right in this particular setting with these indices also doesn't matter. And hence we just get here this product that we cared about. Okay. So to sum up, we've seen this quite foundational chain rule with which you get many more. In fact, you get a few more that I didn't really have time to talk about. And yeah. So the core points sort of that I want to bring across is, on the one hand, that having explicit variational expressions for 3 and more indexed norms gives you a lot of powerful tools to prove these type of general chain rules. In fact, we get sort of a framework for deriving these chain rules by translating them back to norms, and then it seems much more straightforward of how to prove or how to disprove these chain rules. But there is also a problem. And I briefly showed you this variational formula for 3 index norms, but it was not an equality, it was an inequality. We would assume that there is an equality there, but it's not easy to prove this. And for these applications here, the inequality suffices. But if you really want to go sort of give a consistent theory for more than 3 indices, you would want an equality there. So, I mean, this is still an open problem that we're working on. And now you might also ask more generalizations in these operator value Schatten spaces. So instead of considering Schatten norms, maybe we can somehow generalize sort of weighted Schatten norms. And there is, I mean, obviously there is some literature on this, but the applications to quantum theory are not that much developed. So that this could be sort of some path to go down. And the main question, or the main point that I want to leave you with, is can we find further applications of these norms, particularly with more than 2 indices in quantum information theory? There is something that I put a bit under the rug. There is also a very nice way to represent partial traced out quantities in these norms. So we cannot just, we can give sort of the Renner entropy, the Renner conditional entropy, but we can also directly write the conditional Renner entropy of a marginal with like a 3 index norm. And in principle, you can go on like this forever. So there seems to be quite some diversity in what you can represent. The question is, can we find more applications? Maybe this is also interesting to you. And with this, I want to thank you.
Okay, so thank you very much. Are there questions? Comments? Oh yeah. Who was first? Yeah, okay, no, we go back order.
Do you know, so there are other kind of conditional entropies, such as PETS conditional entropies. Do you know whether your methods could say something for them, and also do you expect that similar results could hold for those quantities?
Well, okay, first I would say these are not quite my methods. No, they've been developed by mathematicians since the 80s and then by other people introduced to quantum info theory. But I'm not sure. I'm not too positive on this because this seems quite focused on the sandwiched conditional entropy, and the other, like the PETS, works differently.
Is it also arrow up or also arrow down?
This is only the up arrow. There's only the up arrow. The down arrow is different. It also doesn't work with the down arrow, for example. But sort of one of the things that makes this work is that the index alpha is always bigger than 1 or like between 1 and infinity. For the PETs, you usually care about this being less than 1. Now you could, in theory, I guess, define these operator value Schatten spaces for indices less than 1, and then you get sort of pseudo or anti-norms. I don't think there is literature on this, or this could be interesting, but this seems very focused on these, on the sandwiched and the optimized sandwiched. But thank you.
Yeah, the other question was Lee.
Yeah, so in your the slides you have this chain of inequality showing the multiplicativity. Yeah.
This one.
So this is very similar to what we have a paper on some uncertainty additivity. And you only need the swap is a contraction, right, in this case?
Yes, I mean here, surprisingly, we only swap systems with the same index.
Yeah.
So you don't even need the complete contraction. But
but we know that we have this generalized holder that's you can increase the.
Yeah.
Okay, so but that means that you have some more general additivity, like maybe
Yes.
you can
Yes.
from
yes.
1 to one to QP and with some relation.
I think the p's in principle don't have to be the same. They could be different as long as the p's are larger than the ones here.
Okay.
And I think you don't even need to have ones here on the input system as long as this is sort of increasing.
You just need some order, really.
Exactly.
Okay.
Yeah. I mean, here sort of I presented this with the 1 and p indices because this is what we care about in quantum info. But most of these norm inequalities you can define for arbitrary indices and then see. And usually they hold for indices if the order sort of if there is certain order in the indices. But what exactly they are usually doesn't matter.
Sure. Okay, thanks.
Yeah. Yeah, I mean, here you could see sort of the index of Q1 has to be less than of R2, and the index of R1 has to be less than R2, but then this still goes through. Then the sort of the interpretation as an entropic quantity is less straightforward, but maybe that's also of interest in certain cases.
Okay, I guess if there's no further question, let's thank Jan for those 2 nice moments. And